everybody, welcome to Joshua's YouTube channel. Today we're going to be doing computer science. I do Python coding videos and also computer science videos. So far I've done 8 Python coding videos and two computer science videos. This is my third computer science video. In this computer science video, I will be talking about text, sound, and images, and also be talking about the IEC converting system. Please share this video with your friends, and please watch my other videos on computer science if you like this one. Thank you. Okay, so let's get started. So this is a third computer science tutorial, and this is about text, sound, and images. Okay, so this is what we're going to be covering today. First up, it is character sets, representation of sound, representation of images, data storage, file compression, calculation of file size, ending, and then revision. So it's quite a lot to take in today. So I don't mind if you want to pause the video or if you want to take a picture of some of the slides I've made, so you can revise or you can refer back to it when you need to. So be prepared, because this is quite a lot of things we'll be going through today. Okay, so first up, character sets. So there are three types of character sets, and they're called ASCII, extended ASCII, and Unicode. Don't worry about this for now. First, just read this. ASCII stands for American Standard Code for Information Interchange. So this consists of 7 bits. So 7 bits are like a type of thing for memory. We'll be getting onto it later more when we talk about the memory system. And they can represent most of the characters on a standard keyboard. ASCII can represent most characters on a standard keyboard. Now we move on to extended ASCII. They consist of 8 bits, so from 7 to 8. And they can actually represent all numbers and characters, all English and non-English alphabets. So when I mean non-English alphabets, I mean like in other languages like French or German, there may be dashes or signs over A's and vowels. So those are the non-English characters. And then a few graphical characters like basically like emojis and whatnot. A Unicode is mostly that's what main like big computer firms use. Extended ASCII is for the average person, but average people do have Unicode. So Unicode it has everything, all of the English letters, all of the non-English letters, all of the graphical characters, all numbers, everything. So that is Unicode. So this is the ASCII table. So I just wanted to keep it simple. So this is hex. If you watched my previous video, you know what hexadecimal is, and these are the characters. So the space would be 20. That would be what it would be stored as in hexadecimal format. So there are all these characters. So this is just a part of it, part of the ASCII table, not all of it. Please note. Oh wait, sorry. Please note that these are capitals and these are lowercase. Yeah. So let's go into our next slide, which is representation of sound. So if you were ever paying attention in the science lesson, you would know that sound is created by vibrations in the air. So let's say this video I'm creating right now, right? I have to upload it onto YouTube. But how is the computer storing what I'm saying? This slide will explain. So humans hear things through sound, which is caused by vibrations in the air. True. Sound waves are never the same. I could do many pitches and I could change my voice if I wanted to. This could mean that you never know if it's me or if it's someone else. This is called analogous data. Sound waves can never be predicted because our human mind can do what we want it to. We can make our voice really high or we can make our voice really low. We're obviously not going to say the same things on Skype or on Zoom every single time. So it cannot be a constant kind of variable. It has to be analogous because it can always change. This is a good example. For example, this place goes high, but then again it can go low, then less high, and then low, low. So we can never predict. Sampling is when you measure the amplitude, height of the wave. This is the loudness. So if you look at my pointer from here to the top, this is called the crest. This distance is called the amplitude. So the higher the amplitude, the more loud a sound wave is. Now we use something called the ADC, analog to digital converter, so we can store this sound data. So the ADC works by measuring the amplitude, so this amplitude, this amplitude, this amplitude, this amplitude, at fixed time intervals. So let's say every half a second or every 2 seconds. And then as the exact amplitude cannot be stored and measured, approximate values are measured and stored. The more number of values, so the more number of bits that represent the amplitude, the more accurate the sound will be. So let's say that we have around 128 bits. Obviously that's not realistic, but let's just say we do, representing each sound. You would even hear a pin drop if it was that great of sound, that many bits for one sound. Then we go on to the sampling resolution. This is a number of bits that represent each sample. So the more sampling resolution, the more accurate the sound will be. And then sampling rate. This is a number of sound samples taken per second. This is measured in hertz. So, like we said here, the amplitude of waves are measured at fixed time intervals. The more of those the shorter those time intervals, the higher the sampling rate. The higher the sampling rate. Now that was representation of sound. This is representation of images. So if you stare at your current screen really carefully, you will see many boxes, or if you have a quite old computer, you would see very small circles. These are called pixels. All images are made up out of pixels on the computer. Each pixel can hold a series of different colors. For example, when this whole concept was rather new, like in the olden movies, when they were black and white, all of the images and movies, this is because black was either white or zero, and white was either white or zero. Black was probably 1, and white is probably 0. This is because each pixel only held 1 bit. There is an equation called 2 to the power of x, which you can see how many bits will represent each pixel. X being the amount of digits that represent per pixel. Only 2 were there because 2 to the power of 1 is 2. However, as we progressed and became more advanced with technology, the amount of colors that one pixel could represent grew. Today in modern computers, if you ever see like on PowerPoint or in Word, where you can change the font, there's so many different colors which a pixel could represent. Image resolution refers to the amount of pixels that make up a picture. The higher the image resolution, the greater quality an image will be. So here is two examples of a high resolution image and a low resolution image. You can see that this lotus is in the water is very blurry, and you can clearly see many of the pixels. But here it's you're not able to see all of the pixels because there is a very high image resolution, making the image more accurate. Data storage. So this is the IEC memory system, which I was IEC table, sorry, which I was talking about previously. So this is how these are how they store data basically. A bit is the lowest amount of memory that exists on a computer. Like barely any data can be stored. It's very hard to store data. It's very hard to store data with a bit. A byte is made up of from a combination of 8 bits. Together, one byte can store around a single letter, like a letter A. That's it. According to the more accurate IEC table, International Electrotechnical Commission, 1024 bytes is a kilobyte, and then 1024 kilobytes is 1 megabyte, and so on and so forth. Now, you often might see another table where it goes up in the thousands. It may look to you more simpler, but they just really rounded it. So we normally use the IEC table when we want to get our exact values. I wanted to introduce it to you, or as you might get confused like I did when I was first introduced to the simpler table before, rather than transmitting to the IEC table at first. So this can be measured with 2 to the power of x, x being the number of bytes going up by 10 each. So here we can see kilobytes, megabyte, gigabyte, and terabyte. This is also known as terabyte, the more famous term in the other table, but many of you may have not known that it actually progresses more than terabyte. It goes petabyte, exabyte, zettabyte, yobibyte, and I'm sure it goes on. So you can see that they each times by 1,000 and around 24, 1,024. And this is file compression. There are 2 types of file compression: lossless compression and lossy compression. So lossy compression is normally used when it's not that important data, but you still need to send it across, and you don't have enough data storage to send it. So lossy compression, basically, it compresses it. It has its advantages and disadvantages. Lossy compression serves its purpose better by compressing it more and reducing the amount of storage more and being more helpful to the storage. But it is quicker. But unfortunately, it does permanently delete. Some aspects of a picture or a sound that it cannot be recovered. So it is permanent, and it's not always the best option if you're sending an important document or an important video, which every single detail is very important. Lossy compression won't work well with that. However, what will work well with that is lossless compression. So lossless compression is when data is compressed and it can be reconstructed. It is useful with a very big spreadsheet where there's so many complicated, complex numbers. But it is not useful when you want to compress and quickly and you want to save as much storage as you can. For example, here you can see 190 kilobytes and 178 kilobytes by lossless compression, but lossy compression has reduced it much more to less than half. So you can see the big difference between the numbers here. Calculation of a file size. So this is how you would calculate a file size in an image. So for the file size of an image, you use this formula, the image resolution in pixels, and you times that by the color depth in bits. So they will normally give you that in a problem if you're trying to solve that. And then for the size of a mono sound file, use this formula, the sampling rate, which we talked about before, times the sampling resolution in bits. You always have to make sure it's in bits, because they might give it to you in kilobits or megabits, and you'll have to convert it into bits to use this formula, times the length of the sample in seconds. Again, they will give you the sample rate or whatever they want, or whatever components they want you to, and then you could use basic algebra to get whatever they're asking to in the question. Okay, so as you come to the end, this is an end and revision. So can you guys maybe pause this video and try to answer these questions? If you can, you've mastered today's lesson. What is the sampling rate for a sound file measured in? What is the name of the amount of pixels in the image? What is the name that is the height of the wave that represents the loudness? How many bits in 1 byte? What are the 3 character sets that were mentioned? So it's like in reverse order. Okay, so I'm going to go to the answers now. You can pause if you want. Answers. Okay, so for the first question, answer was hertz. So what is the sampling rate for sound file measured in? The answer is hertz. Then the next question, the previous question, what is the name of the amount of pixels in the image? That is called the image resolution. And then third question, what is the name that is the height of the wave that represents the loudness? That is the amplitude. How many bits in 1 byte? There are 8 bits in 1 byte. And the 3 character sets that were mentioned are ASCII, extended ASCII, and Unicode. So if you got all of those correct, well done. You can post your score in the comments below, and please, if you didn't, maybe watch the video again, or whatever questions you got wrong, go back to my video where I explained that slide. Okay guys, thanks for listening. Thank you for watching this video. Highly appreciate it. Please share it with your friends and family so I can work on my mission to expand computer science knowledge to everyone who has access to a computer. Thank you. Bye.
Have a holly jolly Christmas. It's the best time of the year. Now I don't know if there'll be snow, but have a cup of cheer. Have a holly jolly Christmas. And when you walk down the street, say hello to friends you know and everyone you meet.